Okay, thank you guys for being here for this yet another periodic seminar. Today we have a talk by Alexandre on this paper, how realistic is the mixed criticality American system model. This paper received the outstanding outstanding award at the last ATNS. So you will have around 45 minutes to enlighten us with the research on this topic. Okay.
Okay, so good morning. So as Patrick was saying, the idea is to present the discussion about this paper that we have presented at RTNS. So I think this paper had a good impact in the community and hopefully will be useful to drive new paths of research in this area. So to start, the currently adopted mixed criticality model has been gaining a lot of sophistication. But there are some issues. One key issue is the fact that some of the safety-related standards, the industrial safety-related standards, are not freely available to the community. So typically they are quite expensive, and this resulted in many academic works building on top of previous model and claims. And this is a risk because it facilitates the propagation of misconceptions and drift from the actual standards requirements. And our contribution is to elaborate a bit on those misinterpretations and discuss some motivating arguments for future work. So before we discuss the mixed criticality model, let's do a quick review on the process for the development of safety critical systems, industrial safety critical systems. So the safety critical systems are very present in our everyday lives. And the development of such systems, there are two important components. First, the typical system development process, where we have a phase to where the system is specified, and then the requirements are allocated to both hardware and software, and these will follow parallel flows of development, and are further integrated and validated. In addition to that, in the development of the safety critical systems, there is an additional layer of activities that need to be performed to ensure the safety and reliability properties of the system. So this is an additional set of activities, a lot of activities that need to be performed in addition to the typical system development process. And then, if the certification authority considers that the requirements have been satisfied, the requirement from the standards, if the certification authority considers that this is satisfied, the system is allowed to enter in operation. Otherwise, the system has to go through some redesign until the requirements are satisfied. So this is a typical process, high-level process for the development of safety critical system. Now let's have a look at the system safety assessment process. So this process typically starts with a hazard analysis, where all the hazards associated with the system are identified. After the hazards have been identified, a fault analysis is performed. So we will analyze all the system components, all of its functionalities, and we will identify all the potential faults that are associated to those components. And based on the established criteria, an initial criticality is assigned according to the criteria defined for the project. So typically we have a table like this, where we have the severity levels of the consequence. The worst case typically is catastrophic, and then associated to that we have a criticality category, which is assigned to the components and then to the system. What is important to note is that this initial criticality assignment is done without considering the system compensating provisions, for example, some type of redundancy. So the idea is to evaluate the worst potential effect of those failures. And then we assign a final criticality where we consider those compensating provisions. In each domain, in each industrial domain, we have several standards associated. So in each domain, these standards define different requirements. They follow slightly different approaches and design methodologies, but in essence, they address the same principles, especially in terms of safety and reliability. As I said, it's important to note that these standards are typically not freely available. In some cases, they are freely available. For example, the European space standards, normally they are freely available. The aeronautics are a bit difficult to get. Yeah, so these standards are very important for the development of safety critical systems. And these standards, they establish the requirements for several methodologies and design approaches. Some of them are very well known to the scientific community, to the real-time community. Some of them are not so well known, such as partitioning and graceful degradation. However, the safety-related standards, they do not explicitly specify mixed criticality requirements, but they do specify very stringent requirements in terms of isolation and the independence of between the applications. In addition to that, we have additional challenges introduced by the advent of multicore, and also in terms of resource sharing. So this adds an additional layer of complexity to this problem, which needs to be addressed. And some of examples of industrial solutions that address this problem are the ARI 653 in the avionic domain and the AutoSAR in the automotive domain. Okay, now that we have reviewed the concepts of the development of safety critical systems, let's shift our focus to the scientific work. So most of the mixed criticality work are based on the well-known Gestalt model. So this model established several modes, defines several modes of execution for the system. The tasks are defined using the typical task model with a period deadline and W set, but also with an associated criticality level. So the system starts running in mode K. In case there is some failure, for example, some budget overshooting, the system switches to mode K plus 1, and all the tasks that are not with a criticality not greater than K are suspended and potentially later reactivated. So we are in fact dropping some tasks in case there's some failure. Now let's have a look at some misalignments in terms of terminology. The first one is related to the use of the word function. So in the safety-related standards, the word function is used at the system level to describe some system functionality. And these functionalities are implemented on hardware and software. So this is an important concept which looks at the system level. On the other hand, on the academic works, the word function is used to describe a pure software function. For example, a C function that implements some real-time task, for example. There is also a mismatch of interpretation in the concept of criticality. So clearly in the standards, the concept of criticality is used to describe the level of assurance at which my system must be developed. For example, in the avionic domain, we have the development assurance level, the DAL. In the industrial standards, we have the safety integrity level. So these are defined with slightly different concepts, but in essence, they are the same. So they are used to describe, so for each level, for each one of these levels that we showed before, for example, level A, B, C, D, each of these levels imply in more assurance activities. So it's the verification of the verification of the verification. So it adds additional levels of assurance to the development process. On the other hand, the academic publications are mostly based on the Vestal model, which associates this notion of criticality to modes of execution. So the mode of execution of the system changes, so the criticality increases, and so we have these high and low criticality modes of operation, for example. So there is a slight misalignment in the concepts here. And although these concepts are not fundamentally wrong, they create confusion in the context of industrial mixed criticality system and leads the industrial community and academic communities to misunderstand each other's work. Okay, so let's now have a look at an example to illustrate this confusion between the notions of criticality and importance, which are two different concepts, but there's some mixing between them. So here we have an example from the automotive domain, two functions, two automotive functions here. And in case of a failure, in both cases the car can be unusable, but in one case it can be more severe than the other, but it's still the car unusable. They have identical probabilities of occurrence, but in terms of controllability, in one case the driver can keep the car on the road, and on the other case it's not possible to control the car. So in both cases this function has safety implications. The only difference is that in one case we can control it, and the other we cannot control it. So they are both important functions. Now let's have a look at the concept of criticality. So the criticality according to the automotive standards, here we have the automotive safety integrity level, and it is defined as a function of three parameters: the severity of the failure, the probability of occurrence, and the controllability. So if the driver is able to control the car, the criticality can be lowered. So in this case, according to the standard, since the function 1, the driver can keep the car on the road, we would assign a controllability class, a safety and ASIL level C. So here we have the severity class, the probability, which is the same, and in this case we would assign the level C, and for function 2 we would assign a higher level, a higher ASIL, because the controllability class is different. So as you can see, since both of these functions can have safety implications, it means that we cannot always stop a lower criticality task in favor of high criticality ones. So if we do that, we can have safety implications. Now, another example directly from the EIC 61508, which is the generic industrial safety-related standard. So this example is basically a simple system. We have here the system control function and an error and event logging function. So the logging function sends data to the system control function. So these functions are not isolated. They are not isolated because they exchange data between each other. So in this case, the logging function can help improve the quality of the control performed. Now let's assume that they are running on different hardware in the same platform. So typically the system control function has the highest criticality level associated. And due to the fact that they are not isolated, both of them have to be developed to the highest level of assurance. So this is an important concept. Now let's assume that the failure occurs on the hardware that is running the safety control function. In that case, my system may decide to do a reconfiguration and start running the system control function in hardware B that was running the error logging function, the logging function. So we effectively stop the logging function to be able to run this function. So with this example, which is a good example of graceful degradation. So in this case, we can prove that we can sometimes stop high criticality tasks. So in this case, it's less important, but it's still critical because it's developed to the highest assurance level. Now let's see another example based on the Vestal model. In this case, let's simulate. Let's do here a quick exercise, simulating the failure mode and effects analysis. So this is the typical analysis that is performed on the industry. So here, basically, we want to break some assumptions here. So let's assume a failure mode here, which is a sudden change or unexpected change in the period of the external event that triggers this task. So there is some sudden occurrence, and we initially assume that this task has a certain period, and due to this unexpected external event, the period of the low criticality task will be changed. So this assumption is broken, and there is a change in the period of the low criticality task. However, due to the fact that they are not isolated in time, the failure will propagate to the high criticality task and will affect the response time of the high criticality task. And this may result in this high critical task missing a deadline. In this case, due to the fact that they are not isolated, the low critical task would inherit the criticality of the highest critical task, and both of them would need to be developed to the same assurance level. So in this case, due to the fact that they are not isolated, all tasks would have to be certified to the highest criticality level, and we miss the initial goal of having a mixed criticality system. By using this model, you will never be able to convince the certification authority that the tasks are effectively isolated in time. And as I said, due to the fact that we would need to develop the system to the same assurance level, the cost of the system would increase, and we miss the initial goal of integrating a mixed criticality system in the same platform to decrease the overall system cost. In terms of double set estimation, the Western model and derivatives, they assume that the higher the degree of the level of assurance of a task, the more pessimistic will be the double set estimation. So we introduced, the higher the criticality, we introduce more margin for the double set estimation. However, the accurate or precise estimation of the double set upper bound is a necessary but not sufficient condition to ensure safety. In order to ensure safety according to the safety standards, we need mechanisms to ensure that safety is not compromised in case of a timing violation. So one example of such mechanism is the use of timing partitioning techniques. There is the other research line that has been gaining a lot of focus and sophistication is the use of probabilistic double set estimates. So this model provides a probabilistic upper bound on the execution time, and it aims at building a reliability model for the software. However, software reliability model in the industrial domain is still under debate, and currently, and this is explicitly mentioned in the standards, that such models cannot be trusted yet. So confidence cannot be placed in such models, and this is explicitly mentioned in the standards. So the probabilistic double set estimates is an important research direction, but at least for now we cannot assume that they will be ever used in the development of industrial systems to prove system safety. If we want to follow this line of research, we really need to work on the argumentation. So in the safety-related standards, several of them, they define one very important document, which is the safety case. So the safety case, it's very common in the railway domain, also automotive. So the safety case is like when you go to, like a lawyer to defend your case for the authority. So you really need to build a very convincing and strong argumentation that your system fulfills all the requirements from the standards. So in this case, we would really need to work on this argumentation to be able to convince that the system is safe, in case we want to use this line of research. And to illustrate this fact, so this is a typical question that when we argue with the certification authority, so we're trying to convince them that our system is really safe, and when we are insisting and not being able to convince them, so these are the typical questions that we get. So would you fly an airplane designed with probabilistic software reliability models? So it's really something we need to work on. Okay. So just to conclude, we have shown that there is a clear gap between some of the guidelines provided in the safety-related standards and their interpretation by the academic community. We have discussed some misalignment of terminologies that lead both communities to misunderstand each other's work. We have highlighted the confusion that exists between the notion of criticality and importance. We have also discussed that to ensure safety in terms of timing isolation, we need to go beyond the accurate W set estimates. And we have also shown that probabilistic W set estimates, in case we want to follow that research direction, we really need to work on the argumentation if we really want these systems to be used in the development of safety-related systems. So this is to conclude. Just some additional points in terms of future work. The objective is to develop a new real-time model for mixed criticality, and to do that, which I would like to put this for discussion, probably we need to rethink or even change the way we currently design and perform the safety analysis of safety critical applications that are part of a mixed criticality system. So why these implications? So as we discussed in terms of graceful degradation, for example, if we need to, in case a failure occurs, if we need to drop or turn off some task, that's not, you cannot simply choose one and stop the task. We have shown that this has safety implications. So some functions cannot simply be stopped. So this is something that needs to be addressed during design time. So when we design the system, we need to have clearly defined, so if you want to follow this approach, in case there is some failure, we need to know, the system needs to know which tasks can be dropped. And this has to be also shown in the safety analysis. So when we do a FMIA, for example, this has to be shown in the safety analysis. So we need to show that dropping a certain task is safe for the system. So we drop the task, but we don't affect system safety. And this has to be proved. So this is part of the safety argument that we need to show. So this, in order to design a new, robust mixed criticality model, probably we need to think about this. For example, in a satellite system, for example, so the satellite is it has some autonomy functions, but it's mostly automatic. So when there is some failure on board, one of the modes of the satellite we call it the safe mode. So in those cases, the satellite can switch to safe mode. So in safe mode, what does it do? It disables all the functions that are not essential for the survival of the platform. So all applications are disabled, and only the functions that are really essential are kept. So this is, I would call this let's say, a hard graceful degradation, because you simply disable everything. And but for example, if it's Earth observation satellite or with some scientific equipment, so when you're in safe mode, all the scientific equipment is disabled, and you're not able to collect any data. So it really really results in degradation of the mission, really. So this is an example of how we may be able to address this problem. So but the challenge here is, from the moment that you have applications of different criticalities in the same platform and they need to be isolated, you cannot simply drop lower criticality tasks in favor of the high criticality ones. So this is really a decision that we need to think during design time. Okay, so this is the discussion I'd like to present. So in case you have some question or you'd like to discuss.
So we have time for a couple of questions.
So as you mentioned, like certification agencies doesn't like probabilistic WCT, but at the same time they do accept the safety margin. So what we have is, like, on one side we have safety margin, which is like a single value. On the other side we have the probabilistic WCT, which is the distribution. And basically, can you point from how you understand the perspective why they do like safety margin more? Is it just that safety margin doesn't have explicitly the probability of being wrong? Or it's also the fact that safety margin is already used for many years in the industry, and then they just don't want to introduce something new because, like, okay, if something bad happened, then they might get responsible for this.
No, I would say that the safety, the margins is always mandatory. The margins you must always have.
But it might be wrong, right? So
what I try to explain is that that's a necessary but not sufficient condition to ensure safety. So even if you put a very conservative margin, there is still a risk that at some point this margin will not be respected. And what do you do in that case? So you need to have additional mechanisms to handle these failures. And typically the operating systems that are used in safe critical systems, they have those mechanisms implemented. So typically, in case there is some time constraint violation, some event is typically generated, and it will be handled at the application level. So each system or each project will decide how to handle these timing violations. So in some cases, for example, a level B system, which does not have catastrophic events. So, for example, and this is an example we have on the paper, which is a real case. In the case of avionic GPS receiver to assist the landing of the airplane, it's a system that is normally developed to level B. Because you have other systems to guide. In case there is a failure in that system, you have also other systems. So what happens is, in those cases, one implementation, would be in case there is some error or some failure at some point, an event is raised, and in that case it will be shown to the pilot that at that moment the integrity of that equipment is compromised. So that equipment at that moment cannot be trusted. So since it's a level B, you have to use other equipment. So this is one example on how to handle this type of violations. It can have other approaches as well, but typically it will be the site. You have to, your operating system needs to be able to detect the violation and to raise an event that will be handled according to the system, to the application, and so it's important to have the margins, but it's not enough.
So what you mean is that, in fact, one value is enough. Having a distribution doesn't add anything because anyway they don't even trust that single value already. So because you have to implement these other mechanisms to, in case of failure of that safety margin.
Yes.
So what would be the interest of having a distribution, probabilistic distribution associated with each of the execution time?
Well, this, in my view, this margin, margins mean cost. So the more margins you have, the more costly will be your equipment. So in my view, the probabilistic estimates can help you maybe define less conservative margins, let's say more accurate margins, but it doesn't mean that at some point it will not be violated, because it will at some point. And in that case you need additional mechanisms to be able to handle that. But as I said, probably you don't need to worry much about that because it needs to be handled at the application level. So to define the new model, probably in that model, you only need to be able to detect and report those failures. And you can assume that these failures will be handled at the application level. So for example, dropping some tasks or whatever.
Just a curiosity, so when you say, okay, so you switch to the safety mode because of some failure in the satellite example, but then what? If you switch back to the normal operation, the failure might be still there? It might happen again, or you have overcome the
Well, there are, in the case of the satellite, there is what we call the failure detection, isolation, and recovery hierarchy. So you have several levels of measures that you can take in case there is some failure on board. Sometimes it's handled at the unit level. So if there is some faulty unit, it's handled at the unit level. If it cannot be solved at the unit level, you can, the next level is at the subsystem level, then at the software level, then at the hardware level, and in the last level you have the operator. So the operator, they have full control of the platform, and they may decide, for example, to shut down the faulty unit and use some redundant one. In some cases it reconfigures automatically, in some cases. So there are several mechanisms to overcome these failures, typically reconfiguring the system.
Vincent?
In this work, we have pointed fingers to several problems that are still widely open today. Okay, how to change the safety analysis process, how to incorporate the statistic frameworks. My question is this: like, if you were asked to extend this work, let's say by 20%, 30%, like which open problem, which research direction would you like to elaborate on?
Yes. Probably more conservative one. So you need to have a fully isolated applications. So let's assume that a complete model. Let's assume that, because this is also very dependent on the hardware. So, for example, let's assume that you have a level A hardware, because the criticality levels also associate to the hardware. So it doesn't make sense to have a hardware developed with low assurance level and have a highly critical tasks running on top of it. Doesn't make sense. So let's imagine that you have a hardware developed, a platform developed for level A, certified platform, and you want to run on this platform applications of all safety levels. So in this platform you have level A applications, level B, level C, level D, for example, and the non-critical applications. As we saw in the example, for example, if there is some time violation in the level A applications, which is the most critical, you cannot stop the level B or the level C to have more resources, more processing time for your level A task. So you cannot do that. You can drop the non-critical applications that you can do. So probably, in my view, that would be the most acceptable path. And you would need to incorporate. I mean, this, for example, if you want to, within the level A application, the critical application, for example, if you want to be able to drop some tasks, so those need to be identified at design time. So you can know that you have, within this application, you can have modes of execution, and in some modes you are allowed to drop some tasks. But that will not be the case for all systems, because many systems you simply cannot drop the tasks. Simply, in some cases you need all of them. So you need to have this mechanism to be able to detect the constraint violation and to raise some event and assume that it will be handled at the application level.
So if I understand well, you would like to take the safety critical model, remove all these individual task criticality, and bring back the model to another model which is known as mode changes. So you define different modes of operation, and you ensure that the transition between the modes are correct.
Yeah,
and the system must be aware of all these modes, and then forget about this individual task criticality and things like this.
Yes. This, from an industrial perspective, it doesn't make
because actually this model already exists and has been studied a lot, but it has never been used as a mixed criticality model. But there exists a whole bunch of works talking about this mode change model, where the system can switch mode.
Yes, but you can switch modes, but in any case, the code that you will execute in all of these modes, all of this code have to be developed to the same assurance level. Why? Because this application, all the tasks are not isolated.
So that's why the hierarchical scheduling model can be useful.
Yes, so the hierarchical scheduling can be very useful because it enforces the timing isolation of the application. So for this case, I think it fits very, very well. hierarchical scheduling.
So half of my question was actually answered by Vincent's comment, but so what is missing in the current miscriticality model is the isolation, and also the second property is that not all the tasks should be dropped. I mean, it should be like first we need isolation, and also in the low criticality, some of the tasks should be dropped, not all of them. If you bring these two properties into the current miscriticality system, or in the mode change that there is another model that exists, do you think that it would be close to industrial standards, or we still need something extra on top of this? We need something really new out of the law.
I think it's possible to adapt, but you need to be able to prove that you have time isolation.
Yeah, you need an isolation.
Yes.
You need
Yes.
the isolation between different criticality, different applications, I would say. And then also a better degradation technique that doesn't drop all the tasks, but only drops few, and then readjust its partitioning or isolation, giving more space to the task that requires more resources.
Yeah, what is important here, I think, is to dissociate this idea of criticality and modes of execution. So, if you have a critical application, you can have several modes of execution of this application. But switching modes, of these application switching modes, it will not change its criticality. So the criticality is design time. We need to develop this application. We need to follow the standard requirements, which are very stringent, and we need to have all the evidence that the requirements are okay, the design is okay, all the testing was done, and all of that. So the criticality of these applications and its tasks will not change. You can change modes of execution and drop less important tasks in some cases if your system allows that. But this idea of dropping lower criticality tasks in favor of high criticality ones, this will not be accepted. I'm not sure I answered your question.
Yeah,
So if I ask to correctly, sorry, within a criticality level, you can do whatever what you want to do with your tasks, but you cannot.
You can do whatever you want if it does not compromise safety. So that needs to be demonstrated. If I stop this task,
That's defined by the designer. The designer chooses that.
yes, at design time.
Okay.
And defines and needs to prove. So you need to prove that dropping those tasks is safe. So that it will not have impact in the system safety functions.
Okay, I will put one question also here. You have been addressing mixed-criticality systems at the software level, saying that if I stop some task, I will not jeopardize the scalability of the system, for instance, or the safety of the system. But this problem can also appear at the hardware level, right? Like one core can go off with the same application, with the same criticality, and you will need to redesign for the, let's say, the new or the degraded hardware. Do you think that you can also use, again, this framework of mode change model, both at the software and at the hardware level, or how do you see the combination of the two?
Yes, you need to. I think the example we saw partially addresses this. So you can have some hardware failure, and there's also the satellite example. So in that case, you need to reconfigure the system. So that's typical reconfiguration. So this is what we typically call it the FDIR strategy. So failure detection, isolation, and recovery. So probably in that case, you need to have let's say a degraded mode of operation where you can stop the faulty hardware and reconfigure your tasks to run in another hardware For example, a system with several cores, for example. If there is a faulty core, you should be able to switch it off and reconfigure your system so the tasks can run in the other cores. And in that case, you can decide to drop some tasks that are not essential. But you need to think about that at design time, not at runtime. You cannot take that decision at runtime.
Another question. So, Vincent asked how you can make the model evolve to consider all the requirements of safety-related standards. My question will be the opposite. For what this model that has been used currently for mixed-criticality system, but which is not applicable to, or which is not compliant with the safety-critical standards, for what this model can be useful. So is there already some problems in the industry for which this model can apply, even if it's not related to mixed-criticality systems? Here's the Western model. Okay.
Well, you can use it depending on the domain. Depending on the domain, you may be able to use it. Because in some domains, because there's an important distinction between certified system and qualified system. So, for example, the space systems are normally, at least in the European space industry, the systems are qualified for use in space. They are not certified. We don't have. In the avionic case, it is really certified. So, and also in the automotive, the automotive domain is probably the best industrial laboratory for new technologies and techniques. So, in some cases, where you can demonstrate that the system is relatively safe, you may be able to use this model.
I don't know, can it be used, for instance, for quality of service, for applications that are not safety critical?
Sure. For example, in the telecom domain, you can use it. For telecom applications, for example. Even in the industry, so I think you have several industrial applications that are not strictly safety critical that you can apply.
So mixed-criticality system can be used for non-mixed-criticality systems. Right?
Yeah, because this name is very misleading, because critical system is very generic. Because and this concept, the safety concept and the reliability concept are different things. So you can have a very reliable system that is not very safe, and you can have a very safe system that is not reliable. Typically they go together, but in systems where you have, in case of failure, you have lives at risk, so it goes to a level, a very demanding level in terms of development assurance properties and safety. But you can, for example, the satellite system is not a safety system. It's normally developed to level B. So in the worst case, you lose a lot of money. But typically, satellites don't fall in people's heads. Typically. Sometimes some parts. But normally no. The launchers, for example, airplanes and this, and the cars, which are getting more stringent as well, after some incidents that have been occurred, where people's lives are put in risk because of bad software.
So I think we can stop here and thank Alexandre once more.